Okay, sir. Just give me 2 minutes time. Okay. Uh, Good afternoon to all. I'm just welcome you all for another 5 days program of artificial intelligence in material engineering theory and hands-on practice. The current session was handled by Professor Dr. Chandan Halder. Chandan Halder received his BTech from NIT Durgapur during the period of 2009 and completed his MTech and PhD from IIT Kharagpur in the year of 2011 and 2016 from the Department of Metallurgical and Materials Engineering. During his period of PhD, Sar has visited AGS University of Science and Technology, Krakow, Poland as a visiting scientist for 2 years during the period of 2012 to June 2014. During the visit, he worked on developing a multi-scale microstructure evaluation based phase transformation model of dual phase steel. After completing his PhD, he joined as a manager of R&D department from the Misra Dattu Nigam Limited, which is called as a Midani from Hyderabad for the period of 6 years. He is now currently Sir is working as an assistant professor at IIT Indore from the period of July 2022. Sir's current research interests include magnetic diffusion modeling, multi-scale finite element modeling, and then modeling and simulation of microstructure evaluation, and also neural network-based alloy design. During this period, Sir has published around 15 papers in reputed peer-reviewed international channels. I'm just once again welcome you, sir, for the current presentation. The stage is yours, sir. You can start the presentation now.
Yeah, thank you for a nice short biodata. Thank you. So just before going further, just want to ask that am I audible to all? Can you confirm that?
Yes, sir. You are still
Yeah.
audible, sir.
Okay. Okay. Yeah. So I just share my presentation.
Okay, sir.
Is it audible? Is able to see
Screen
my
is visible, sir.
presentation?
Yes, sir. Screen is
Visible.
visible.
Okay. Okay. Yeah. So as you have heard, that my name is Chandan Halder, and I normally working on the mainly the diffusion modeling and microstructure modeling, and some sort of alloy design using data, using some sort of data. So yeah, today my presentation will be going around the like what is actually this data driven modeling, and how that is been driven, and what is the use of evolutionary neural networks, like what is actually evolutionary neural network. And before going into the evolutionary neural network, I just touch upon the artificial intelligence neural networks, because without ANN, it is very difficult to understand the evolutionary part of it. And at the end, just to give you the some applicability of this kind of that data driven modeling, I have like applied it to some industrial data at my period in Midhani. So I will present that how you can able to use this kind of algorithms in your daily data what you are going through like all the time. Yeah. So let's start. Yeah. The first thing is, see, I am from the metallurgical background, and I have more than 6 years of experience in industry. So I can tell you one thing, that in the metallurgical industries, the data, there is no shortage of any kind of data. So if you visit any shop floor or any industry for that sake, and you will see that lot of data will be generated even every second, you can say. So this all coming into that big data concept. Big data is actually that this extremely large data set what you are generating every time, every second, how you can able to analyze computationally to predict some kind of patterns into that. Like you are generating something and you are doing the same mistakes day after day, but if you able to predict the pattern, like what is going behind, like what this is, if some problem persists for a period of like for some years, like how that how the data will reveal some patterns, trends, and something that will give you some idea about probable reason behind such kind of problems associated with that. So that volume, I already said that industrial data is having humongous volume, and the diversity is of course because in the industrial side, if you see that it is having a very diverse nature, and not even like diversity in the sense of not in metallurgy also. Like uh, if you are sensing that, like even in in other fields also you can apply this kind of big data concept, and you have to again check the pace, variability, accuracy, and all of this. So this is all about the big data thing. Now, suppose you have the data with you. Now, you have to first understand that which category that data belongs to. So for that, first is the supervised learning, and the second is the unsupervised learning. So this mainly this is the two type of learning you can do on that data. Supervised learning, as you can able to like even predict also like what going to be a supervised learning. Like it's like simply if I have to say that supervised learning, where you have the models where you want to train, and those data what you're using are labeled data. Labeled means in the supervised learning you have both the input functions and the output variables in your data set itself, and you just want to map that what is the variability in sense of input data on the output variable on. So this is kind of kind of like what we are doing. Like for the alloy design we are actually doing the supervised learning because we want to know that how our output we want to improve. We know the output of the given data set, of the given input set, and that output we want to analyze, and that output we want to improve it. So that is supervised learning. And in the supervised learning there are two kind of majorly there are two kind of classifications. One is itself called classification learning, and it is the regression. I think you have all of you have heard about that. So unsupervised learning, if you say, unsupervised learning is something where you don't have any output on that. Like you have a data, just a data, and you don't know like what is the output of that data. So that is unsupervised because you don't know that what you are targeting, but you are doing the analysis so that you can able to make some sort of grouping. So it's kind of like you have a huge data set with you, and you just want to do the unsupervised learning because you don't know anything about the data. So in that sense, you want to group, like like you want to have a different groups of data so that you can able to say that this group belongs to this kind of uh, learning, and then other group belongs to other kind of learning, and like that. So majorly these two things are there. Now in the unsupervised learning there are few algorithms called clustering, and like association is again one of the unsupervised learning data. As I said that the classification algorithm is actually where the model tries to predict the correct level of given input data. So this is what the classification is, and I'm not going deep into that because uh, we have to cover a lot of neural network in this presentation. And of course the regression, you know that you have a dependent variable and you have associated independent variable, and you want to know the relationship among the two of that, both the independent and the variable and the independent variable. So this relationship you want to that understand, that is using regression. There are many types of regression, like linear regression, polynomial. I think many of you have heard all this, support vector, decision tree, random forest. So all these are different type of regression models where you just want to map between the two variability, like both the independent and dependent variables. Now if you go to the unsupervised, there are a lot of like a lot of clustering kind of data. Like there are very commonly used data called that k-mean, distance-based k-mean, like where the centroid, like you have a bunch of uh, huge data where you want to know the grouping, because you do not have any idea about the data. So just and at the very beginning you just want to do the clubbing, like you want to do the grouping of the data. So k-mean is one of the very like popular algorithm there, where we're able to make the cluster out of the data, so that cluster can able to make your classification of the data, like that one group belongs to certain properties, other group belongs to certain properties, like that. So yeah, and this is something k-mean. You, if you want to, like, there are you have to k clusters means you have how many clusters you are able to form. That is the k, that amount of k, like yeah, that k value. And now you want have you are, there are different centroids you have to form, and the centroids that centroids is actually the one, like suppose you are making two different centroids at two different locations, that Euclidean distance I'm talking about. And that centroids, that where whatever data is close to that centroid is belongs to that cluster, and the other centroid whatever close to the other centroid, that is belongs to that cluster. So now once that is set up, then the data which is belong to the first cluster, then you take the mean, then you adjust the Euclidean distance of the centroid, and like that, like vice versa, you'll able to see that, like one like data are able to group together, like some data are passing from one cluster to other cluster, like that. So eventually you will get some sort kind of clustering there. So you'll able to find that some grouping will be there after performing this k-means. Yeah, so the data mining process will come into that. Like there is a process of problem formulation. Of course, when we have the data, like first you have to understand that what problem you're targeting there. Like that data is have, like you have to understand first. You have to first digest your data first. Like you have to understand each and everything there. Like what you want to do with the data. Like what will be your output, what would be your input, what the things you don't want, what the things you wanted. So all these things is there. Problem formulation, of course, you have to understand first. Then the data collection. Yeah. Then there like what kind of data you want to collect, like how much you want to collect. Like there are, like suppose if you're in the industry, there is no limit for the data collection. So where you want to stop, like all these things are there. Then the pre-processing, like uh, you will see that all the mostly the industrial data are having a lot of mm, lot of you can say the outliers. So how you are able to clean those outliers, then duplicacy of the values, some missing values are also there, how you are able to fill those missing values. So these are called the pre-processing, cleaning, and transformation. Like you do some sort of algorithm and check how you are able to map different things there, and you are able to predict something out of the data or not. So of course that mining task and mining method is there, and eventually you will end up with the result evaluation. So you have to do the result evaluation and proper visualization of the data. Yeah. So coming into the main part of the today's talk, that is data driven modeling. So data driven modeling is the part of big data only, where you have a data with you and you just want to know that how much like what is the pattern, and like I'm talking about the supervised learning right now. Suppose you have an alloy with you and you have the manufacturing processes all related with that alloy with you. Now you have to target first, like in the problem formulation you have to understand that in the problem formulation you have what you want to target. Like suppose you have a bunch of suppose steel data with you, and just or a particular steel data with you, and you have a lot of like manufacturing data available for that particular steel, particular grade. uh, so uh, is that now you have to find first the problem, that like what you want to achieve out of that data. Like suppose it has this ys value, uts values, then all the melting related values, then all the suppose it gone through rolling or forging. So all those values are there. So first you have to identify what target you want to to, like suppose you have achieved, you want to set that, no, I just want to have a better property in terms of strength, in terms of ductility, like that. Or if you are if you are suppose targeting the melting parameters, then you want to have a better melting properties, like better melting time, better melting efficiency, like that. So first you have to formulate that, and after that, once you have the data with you, now you have to find the proper algorithms which can able to give you the proper analysis, proper patterns on that particular data. So uh, it is mostly the last part, like the data source. You have to understand the gathering, that exploration, the modeling, and the validation part. Now, I just want to touch upon one thing before going further into the evolutionary neural network. That will come later. I will explain what is evolutionary there. But before that, like just I want to touch upon the part of artificial neural networks. Like I think all of you have at least once heard of the term artificial neural network. But I suppose like a lot of you may not have the idea that, and maybe all of you are thinking that a neural network is something, a black box where you just input some data and you'll get some output out of that. So nobody actually cares about what is going inside that artificial neural network side. So it is basically just I just want to touch upon like how actually what is going inside the neural network. So architecture wise, normally a very simple architecture of neural network has three things. One is the input layer, where in this diagram we can able to see that x1 and x2, that these two round circles, these are represents your input layers. Now then there is a hidden layer where these circular things are called the neurons, and the output side is called the outer layer. So this mostly this artificial neural network of very basic network is comprising of only three things. Now there are evolution of neural networks also, where now you are able to see that there are a lot of hidden layers there inside, in between input and output. Now here is only one hidden layer, but in the suppose in the convolution neural network, you'll find like three or four layers of hidden layers in between. So that is okay. Uh, Once you able to understand the very basic of that, I think it is not a very big thing to understand the next difficult complex part of it. So first, a very basic neural network actually is suppose this x and 2. That's suppose we just want to process the your suppose or get output, like we'll come into that. First we see the architecture of neural network, that each and every input, suppose x1, here only two neurons are there in that hidden layer. So each and every like input is connected to each and every neurons, so in the hidden layer. So here you can able to see that the x1 is connected with z1 and z2, both by the weights w11 and w12. And similarly that x2 is connected with both the neurons with the weight for the recognition purpose w21 and w22. So these are the weights, these are the random values, which is like these are always in between 0 to 1, and these are the random values which are set initially at the onset of the like uh, uh, onset of the process. So now once that thing, all this input going into that neurons, now that neurons is again connected with your output, and this output is connected with again some w, again some, these w's are called weights, again with some weights. So these are again the random numbers between 0 and 1, and this output, there are these output are actually some activation functions. There are a lot of activation function we will see when we go along. There are a lot of activation functions there. Like some are using the sigmoid activation, some are using some different activation. So we'll see. Like this is normally the basic architecture of the neural network, and here each and every neurons and inputs are connected with each and every other side of that layer. Now, I just want to model. This is actually outcome of an OR gate. If you know, remember that it was 000, 101, 011, and 11 is 0. So here uh, we just want to model. No, I think there is a. Just want to model the last one, that 110, not the 011, but 110. And suppose here only two inputs, x1 and x2, and we are using three hidden neurons. Like in the hidden layer, we are using three neurons. So each x1 and x2 are connected with three neurons. So each x1 is connected with all the three neurons, and next x2 is connected with all the neurons of the hidden layer. Now that all the hidden layers are connected with the output layer, and everything is connected using a weight. So these are normally, there are basically two steps in that. One is that feed forward network, and another is that back propagation network. So first we see what is going on, what is going when the feed forward network is there. Like now, suppose just we want to model our last outcome, that 110. So our inputs are, suppose the 1 1. So here are the inputs. So if you see, as I said, that all the inputs are connected with each neurons. So each are having different weights, and these are all random between 0 to 1. So this random weights in the hidden layer, it is connected. Like suppose this first connection is having zero point 0.8 weight, second one is having zero point 0.4, third one is having zero point 0.3. Similarly for the x2, first is zero point 0.2, next is zero point 0.9, and next is zero point 0.5. Now this is your input, random input layer. Now uh, as I said, so what happens, like suppose in the first x1, it is connected with all the three neurons. So the hidden layer neurons will calculate this part. So calculating this part means each neuron, suppose first one, that each neuron, if you take the first neuron, then it will having a value of x1 also, and having the value of x2 also, and x1 is having the value which is connected with the weights zero point 0.8, and x2 is connected with the weights zero point 0.2. So it's basically it is taking the summation of both the things, and it will become 1 here. Similarly for the second neuron becomes 1.3 based on the random weights here, and last one becomes a zero point 0.8 here. Now once this is calculated in the hidden layer, it has been now, since the feed forward, now it will go to the output layer side, and the output layer is actually the activation function, and it is a sigmoid type. Suppose sigmoid type can have the relation is like that. Like sigmoid can take the relation like 1 by 1 plus exp minus z. So if you take this, and if you take the neurons of each of this z is the value of this particular hidden layer neurons. So if you calculate then the output activation sigmoid will come out like this one, 0.73, 0.78, 0.6899, like that. So, and suppose this activation function again is connected with some weights with the hidden layer. Suppose the connection is 0.3, 0.5, and 0.9. And if you add everything like output value, then you will able to find that it is coming around 1.23321. And your output sigmoid, if you again calculate that part, your output sigmoid becomes 0.7743807. So now, as I said, that it is saying 774 is your output value of the sigmoid. Now, as as we are want to model our things for the 110. So we want our output as 0. So it is completely wrong here. So model 0 means it is coming 0.7743, which is not correct. So what we'll do, it will do the back propagation for that matter, so that it can able to change all the weights, both the this weights and these weights, both the weights, so that it can able to get a value, that output sigmoid value, where it can get the probability like point less than zero point 0.5. So in the probability function, if it is less than zero point 0.5, then that considered to be as 0. Otherwise it is considered to be 1. So the value right now 0.774 actually is reflecting 1. So instead of that, it will change your weights accordingly using the back substitution, so that it can able to change the weights with the weights of the connections, and simultaneously your your output values, so like this. So for this reason, if you check that error right now is completely this one, because we want a 0 value here, but we get some values here, so that becomes completely your error values. Now after that, next is the back propagation method. Here, uh, the back propagation side, first you have to do the derivative of the sigmoid. It will take this kind of relation, where this that function you have said like there, that it becomes your sx. So if you take that, this becomes your derivative of sigmoid, this value. Then you multiply this error with the derivative, that this value with the error value. If you multiply, this is becomes this one. Now that particular error you're calculating from the derivative, and this, if you multiply this, you're eventually getting this value, and this if you divide with your original sigmoid, then you are actually evolving this kind of values. And then if you take that like addition of the last column and the actual output weights, if you do the addition, because it's a minus sign there, so all becomes lesser. So your weights becomes 0.11493, which is, suppose for this reason it is zero point 0.3, zero point 0.5 and zero point 0.9. Now that is changed to 0.1149, 0.3278 and 0.7039. This is the output weights now change. You have changed the output weights. Now there's some adjustment you have to do for the change of the input weights also. So like that, if you divide the second column by the actual output weights, then you are eventually getting some value. Then the multiplying last column with the derivative of sigmoid, if you do that, then this delta input weight. So you have eventually getting this kind of errors. If you do the addition, then you will see that your new input weights is modified like 0.711 instead of your zero point 0.8. So instead of zero point 0.4, it becomes 0.35. So instead of zero point 0.3, it becomes 0.26. So everything reduced, because you have to get a 0 value at the output, and that you will only achieve if you able to reduce your input weights. So the now this neural network will understand that it has to reduce its weights of the connections, and it is eventually doing all this calculation so that it can able to reduce the weight. So if you put this new weights of your input layer and neurons, and this new weights for your output layer and neurons, then you will see that if you implement this again and do the same sort of like calculations again, you will find that your errors will reduce further, like from 0.77, maybe the next step it will reduce to zero point 0.7 in the next step. If you keep on repeating this step, so what we have done, like what I have shown here, this feed forward and back propagation thing, both if you combine, this becomes a one epoch. Maybe you have heard, you have somewhere seen that one epoch means one complete that complete feed forward and back propagation is completed, and this becomes one epoch of that, like some kind of generation, like one iteration, you can say one iteration is completed. So with that, this new inputs reduced, and if you do further the next to second epoch, then you will see this new inputs will decrease further, and it will keep on decreasing till the time it will reach your output value 0. So it is the way that neural network is improving. It waits and try to capture the output value. So this is all the supervised learning we are talking about, because we have the weights, we have the output with us, and we just want to map with our output layer, with our outputs with that. So this is the fundamental of ANN, how ANN actually works inside, like how it is taking all the values and how it is mapping all the output value on that. So this is just to show you that in order to uh, give you a clear picture like what is going inside a neural network there. So yeah, so with this it is can get up to your whatever you want to train your results like x1 x2 with y, it can able to predict that. Now as I said, that output layer is having activation functions. So that's just you have seen the example of the sigmoid activation function, but there are other activation functions there also. Like there are linear activation functions you can select, then hyperbolic tangent you can select, then rectified linear. All these are different approaches for the activation functions for calculation. Now, of course, there are some pros and some cons are always there. Pros are that it can learn more complicated class boundaries, as you are seeing that like when some error is coming mm, there in the neural network, it will adjust its weights so that it can able to come close to the actual value. So it can learn more complicated class boundaries, and it is a very fast application, can handle large number of features also. um, Cons are always like a very slow training time, because it takes time, hard to interpret, like hard to interpret for the neural network. Neural network doesn't understand the physics of your problem. It will only understand the data. It will only understand the architecture of your neural network, and with that architecture, how the data, if you input, how that will be processed. So it will not understand what physics are involved with that data. So you have to always understand that like it is very hard to interpret. Like neural network never able to interpret that thing. So it is the user who's using that neural network has to interpret for that matter, and how like trial and error for choosing number of. So these are always there, like as you can see that like if you're able to increase the hidden layer neurons, then you can find that you will get eventually better like convergence in a little iteration, and becomes faster also. But it is always not the truth. Number of nodes are very important, and if you do like if you like overemphasize it, then it will not give you a proper result, because it takes a lot of time in that sense, because a lot of calculations, when one neuron addition can put lot of computation burden to your computer. So you all have to understand like how the trial and error for choosing this number of nodes there. So these are all very difficult things, and you have to like with time you have to understand everything, like how you are able to process all those things. Now comes to the evolutionary side of the neural network. Now, as we have seen in the artificial neural network, that ANN takes like here ANN is taking all the data and is able to try to train the data, try to learn the data within itself by changing its weights, both input weights and both the output weights. So it is learning by changing the weights. But evolutionary neural networks are little different in the sense like it will not just will understand the data. That is there is a two part in the evolutionary neural network. One is the like one is a training part, like it will understanding your data. That is your basic ANN, what you are doing. now. But like furthermore, it will add optimization part on also there. Like I will explain more precisely. Like evolutionary term here is for the evolution, which is the evolution in terms of biological evolution we are talking about. So suppose if you put some biological evolutionary thing into your neural network, then you can able not just able to train the data, but you can able to optimize the data also. So that is the basic necessity of evolutionary neural networks here. Now what happens, like yeah, so before going further for the evolutionary part, first you have to understand what is the uh, concept of Pareto optimality. So Pareto optimality, like it is always a set of non-dominated solutions. Like suppose I give a very basic example. Suppose there are two students, both are appeared in two different exams, in one in English and one suppose Hindi, and one is Ram and one is Sham. Both appeared for the English and Hindi exam, and suppose Ram got higher marks in English and Sham got higher marks in Hindi. So both, you cannot say whose is better than other. So it is like both are better because both are non-dominated solutions. So in that sense, suppose if a third person is there whose like whose English and Hindi both are inferior to the uh, Ram and Sham both, then that becomes your uh, dominated solution. That those two, that particular student has been dominated by both Ram and Sham. So to better understand, like its Pareto optimality is containing the non-dominated solution. Suppose whoever you are staying there, suppose you want to travel somewhere. Somewhere means you want to travel to suppose Delhi. You want to travel now. There are a lot of ways to go to to reach Delhi there. Like so the ways are like you can travel by car, you can travel by bike also, you can travel by bull cart, you can travel by flight, you can travel by train also. So if your objective is like if you map this to this F1 and F2 in this particular image, if you map like F1 is your like cost and F2 is your time, then you can understand that suppose if you take the flight, it will take you a lot more cost but take less time. But suppose at the same time, if you suppose going through the bull cart, then that will take you lot less cost but very high time. So all the solutions there are non-dominated because if you take both the objectives, like we are not talking about the single objective function here. This concept of Pareto optimality is always there for the multi-objective, mainly for the bi-objective problems, and both objectives should be it should not be dependent. It should be independent objectives, and both objectives should, if some solution is is actually performing better in both the objective, then you can say this is non-dominated solution. So if you take the example of traveling to Delhi, then this flight, then this train, all will come into that non-dominated this blue line because if you take if you take the cost, then flight is the highest, so it was inferior to train and car. But if you take the time, flight is having the best, plane is having the best possible that way of travel in very short time. So you cannot say, if you take both the objectives, you cannot say which is better than other. So in that condition we call it the non-dominated solution, and it will take the front. Like if you see the blue line, it will take all the front. Suppose these are all dots, and if you want to map that dots, like These dots are like flights, the train, then like the cars, then bull carts, and like that. So suppose what happened? Suppose if I'm taking the train for that instance, there are a lot of variety of trains are available. I think so. Uh, so there are like Rajdhanis are there, like all these things. There are very fast trains and some slow trains are also there. So in that sense, in that category, if you check that, uh, suppose in the train category, like if you have the Rajdhani, which is taking lesser time, a little costly, but lesser time compared to the other very slow trains, which is taking you less cost but more time. So those becomes little inferior to the Rajdhani side. So if you take that front, that it will not able to come into that non-dominated solution part. Maybe those are these red dots I'm referring to. These red dots are all those dominated solutions, because if you consider the cost side, this Rajdhani fare and that particular the slow train fare is not very there is not much difference there, but there is a lot of difference in the time. So these becomes the dominated solutions. So those solutions is dominated by this part kind of blue lines, blue solutions. So this is the concept of Pareto optimality. And all the evolutionary neural network, when we set the objectives, which is which should be it should be not dependent, it should be independent to each other. Something like suppose if you take the metallurgical example, it is like if you take the Hall pitch relation. So all we know that if you grain size reduces, it is increasing your strength. But suppose somebody wants a better strength at higher grain size. So kind of an inverse Hall pitch, but not in that part, but something which is not possible. Something it is possible, but something which is very difficult to achieve. So these kind of objectives, that those are not very dependent on each other, that kind of objectives are very important for the evolutionary neural networks. So evolutionary neural network, as the name suggests, this is biological evolution there always. And in that one, it is again part these three layers all there, and you take all these inputs in the input layer, this x1, x2, x3, whatever, or how many, whatever inputs are there, but it will take the two output layers. It will become the bi-objective problem, because you want to do a conflicting objectives to solve, and conflicting objectives are the most difficult and most challenging in the world to solve it. So this will take this y1 and y2 as your conflicting objectives. So one catch is there, like how it is different from normal ANN is that in the ANN, each and every neurons is connected to each and every inputs, but this may not be the case with the evolutionary neural network. It can evolve, like evolutionary neural network can change its weights with complexity. Um, suppose in the evolutionary part, we are not talking about one particular evolutionary neural network, but a set of a set of a bunch of generations neural networks. Suppose you set suppose 300 neural networks. So 300 different neural networks are there with the different architectures. So in the neural network side, evolutionary neural network side, that the lower part, the input and the hidden part, this lower side connections, that uh, input to hidden layer connections, these are all not fixed. Fixed means all may not be connected. So based on the complexity of the problem, it can change. It can connected or may not connected with the hidden layer. So this input and hidden layer, there is a maybe you'll find there is a gap there. Like some inputs may not be connected with the hidden layer always. Like all the neurons, in fact, no, it is connected with the hidden layer, of course, but not with all the neurons. So that is the basic difference of evolutionary neural network. And with this only, you can able to check the difference. Like uh, suppose uh, you will find that some neurons are not connected to some inputs, and how that neural network is performing in the fitness side, then you can able to see that how that that particular input is important for the objective y1 and y2 or not. So all these things are there. Like suppose x1 uh, in this example, in this figure, if x1 is not connected to suppose neuron 3, and still this neurons is performing better, this neural network is performing better in terms of other, this terms of y1 and y2, then you can always question that this x1 may not be important at all for the problem. So all these things is evolving with the evolutionary neural network. And before going into that, like there are few things which are very important for the evolutionary neural network, is that first is that elitism. Like suppose in that we have seen that that non-dominated solutions you wanted, and this non-dominated blue line front, as we seen in the last graph, these are all are elite solutions, and we don't want to lose those elite members, because now we are talking about a generation, we are talking about a population of neural network, but not a single ANN. We are now talking about a population, and population is something where each and every neural network is differ to each other by by its weights. Like what some, like suppose if some neural networks are connected to all the neurons, all the inputs are connected to all the neurons, maybe some neural networks no, maybe it is missing mostly any connections. So it is like that, like this variability in the neural networks. So with that, we don't want to lose the elitism also, like we want to preserve the elitism. And when we when we are talking about that objective y1 with y2, then we always want to know that how you able to evaluate that, like that suppose this particular neural network is important or not important, then how you will able to analyze that. You will be analyzing using some fitness assignment, so you will give some basic value to that, some ranking kind of thing, where that rank, with the rank you can able to see that whether it is a non-dominated solution or it's a dominated solution. So everything, like if you want to know the Pareto optimality there, then you can able to understand that how that particular neural network can have the fitness value. So there is a particular there are a lot of like mm, you have to assign some fitness to each and every neural network, so that it can able to sense like what is the fitness value in terms of both y1 and y2 fitness, in both in terms of y1 and y2. And if objective changes, your fitness also changes, so keep that in mind. So fitness assignment is there. So there are famous like Fonseca, Fleming there, so they are uh, they have proposed some fitness assignments, so like that. And since it's an evolutionary neural network, there is always a scope for evolution, like how you are like naturally mimics your evolution of the neural network. So here uh, it is taking the help of genetic algorithm, where it is one part is called a predator prey genetic algorithm it is taking. And in this algorithm actually it is taking a two-dimensional computation domain space in the form of grids whose ends are contiguous in nature, is constructed to imitate the real life hunting of prey by the predator in a forest. So this random distribution of prey and predator are there. The two inhabited species considers predator and prey, and this in the small form it is called PPGA. This PPGA represent a mathematical construction of lattices for smooth functioning of the algorithm. And PPGA is purely computational space it is taking, and any member of any prey population, all the, suppose here the all the prey we are calling, all the prey are your neural network population. So all these are called preys. Now, if we just want to have a particular predator, a certain entity which can have a certain like hunting rules there to hunt the predator, so hunt the prey. So how predator hunts the prey with some basic rules there. So any member of the prey population differs from any by its see, yeah, any member of this prey population differs from by its lower part connections and the weight values associated with them, and that will give you the fitness value. So suppose one particular predator is surrounded by four or five preys. So during the hunting, it will hunt the most inferior solution based on the fitness value with respect to y1 and y2. So that fitness value will be killed, and it will retain all the elitism in the population. And there is always a target prey population size, so that the prey population may fluctuate, but it can eventually during the competition it will always like recalculate the prey population size. And if it is something, if it is suppose it is growing very fast, some sort of measure should be taken so that it can be restricted within that population. So predators, on the other hand, are external entities introduced in the crate for killing the bad prey, as I said, based on the fitness values evaluated on the basis of the objectives. Now, this is the hunting rule you have to set. And with the hunting rule, uh, actually, what we want to do is that with the hunting, we just want to kill the weakest prey. And killing the weakest prey means you are eliminating all the dominated solutions there, and you just want to keep all the non-dominated solutions there. So, in that sense, you are able to remove all the bad solutions out of your system, and you just want to keep all the better solutions, population of better solutions. So, there is a basic hunting rule for the predator prey genetic algorithm. And with that, once you have achieved elite group of population, uh, in a population the elite groups are there, then we always do like in the evolutionary neural network there is always a side for a diversity. So it elitism doesn't mean that it should be like, if I take the example of that plane and train, it should not be always towards the plane. So elitism is like, it should maintain the diversity also. That bull card will also be there in that list. So elitism should be maintained, but with not with the without any hampering your diversity. So diversity, to retain the diversity in the evo and like this evolutionary neural network, there is a there is a possibility there. If you cross over to the two better, suppose once you have done the killing using your predator prey genetic algorithms, now you have the elite members in your population. Now you can do the crossover with that. Do the crossover means you just exchange the neurons, one particular neurons with the other, and you retain both the parent and the offspring also. So there are some rules for the mutation and for the crossover. And this crossover is between the elite members, but maintaining the diversified members there. And once this crossover is done, you can ensure that this crossover can have a solution towards a better outcomes. Now, uh, once in a while, we do the mutation also. Mutation is a tweak, like suppose tweaking some part of the neurons or some weights. So mutation is something where it tweaks some weights of the connections, and it can, that weight can maybe result into inferior solution, or that tweaking may come up into a very good solution also. So all can matter there, like the lower part of that input and hidden layer there, this all the tweaking of this crossover and mutation is taking place, so that it can eventually get the mutation is always uh, there. Like there is high possibility that you can able to like you are actually make that particular solution inferior. But it is not always the case. Like once in a hundred time, we are able to generate a very good solution out of that also using the mutation. Like you mutate one weight of a particular connection between input and output. So with all these things, you can maintain the diversity in the evolutionary neural network using the crossover and mutation. And you can, of course, the test the data in that there you can able to divide the data into three different parts, and there is some overlapping, and you can always check that overlapped parts whether it is matching with the other sets or not. So it is the data one is matching with the complete data set or not, data two is matching with the complete data set or not. So all these things you can able to check using this testings. And now uh, comes to the next part, like how I have implemented the evolutionary neural network into results. So here in the data driven modeling which I have done, so this is for those who are not aware of Mithani at all. So Mithani actually making lot of specialized steel, titanium alloys, super alloys, and they're like other like hafnium alloys. Like there are like soft mag alloys, something like that. So it will have like lot of you can say diversity in the field of alloys. In Mithani, it can have the special super alloys, titanium alloys majorly, but apart from that also it is can have the like other different alloys also, like as I said that hafnium, then cobalt, like all these things, cobalt based alloys like that. Now if you do the melt if you do the product side of that, Vidhani can have the melted products, the forged products, and rolled products, and the drawn products. So all these products it is supplying to the customer in different forms. Like some are with only the melting, some are with only melting and forging, some are with both melting, forging, rolling, some are gone through drawing also, and this supplying to the customer. Now, if you process flow chart, if you see, Vidhani is having this sort of primary melting units like electric arc furnace, then air induction furnace, then uh, then LF is there, that lateral furnace is there, then VD is there, then vacuum induction furnaces are different capacity is there. Then there are some secondary melting units are there, like vacuum induction refining units are there. Then electroslag refining are there. So these are all these are all melting side. These are all there. Now, now there are some forging equipments like forge presses are there, forge bars are like forge presses are like two different forge presses are there. One is 6,000 ton and one is 1,500 ton. One ring rolling there, and the rolling side they have a lot of roll mills. Like one is the hot and cold roll mill is there, and one is the bar and rod mill is there, and some wire drawing equipments are also there. So this is the basic outcome of that. Now, if you see the for the from the customer side, that like customers demanding a lot of specifications out of Midani, because Midani is customized. Midani is always making customized product, and there is always like alloy chemistry like challenges there with respect to the reactivity, the solidification behavior, the retention, elimination of specific elements like that. And customer are very much keen to reduce the residual gases, trace impurities, inclusion content, and better mechanical properties like that. So these are all the asking there from the customer side. So application, if you see that very high temperature application, high stresses application, very severe atmosphere applications are demanding those particular materials. So like is all that making this kind of products, these kind of alloys are very challenging always, because it is completely like taking a lot of like understanding to do this kind of uh, this kind of melting practices and all these manufacturing practices there in the Midani. So this customer side that imposing restrictions on the chemistry, then macro chemistry, then macro structural restrictions there, then non-metallic inclusion level restrictions are there, then microstructural restrictions are there. So in there, we have taken up a project based on the maraging steel. Maraging steel is a special steel uh, where it is with after aging treatment, it becomes very hard. Can retain, can gain strength more than 1500 also, like a megapascal. So it is a complete thing. Like just we start like as I was there, I was started with that thing like as the primary and secondary melting started. Like we started collecting the data out of that, and with the forging, and consequently that we were actually uh, taking the forging and rolling data also in our practice. So we started the primary melting VIM. So this margin steel is going through the vacuum induction melting, because it is not a normal steel. It can go from any electric arc furnace, and because there this gases impurities levels to be checked every time, and that to be retained at a very lower side. So to maintain that, this VIM furnaces are there to get all those primary melting things. So so we collected the data from different records of there, some physical there, some online there. So we collected everything from that, and we compiled a data set out of that. And as I said, the pre-cleaning is required always. So there are all like there are all duplicate datas involved. There are all maybe missing datas there. So we have to fill all those things. We have to like all the duplicates you have to eliminate, all the unfilled datas you have to like do some sort of analytics there, so that you can able to fill those data. So all after do all the cleaning, data cleaning, we do the feature engineering there, like what kind of featuring we want out of the data, and that our problem statements, and we do the like then we able to analyze that what we want to apply. Like so with lot of discussions, we come into like conclusion that we want to going to have the evolutionary neural network as our primary algorithm there, so we can able to generate whatever data we have generated out of our this thing, our process manufacturing and margin still, we will input that into the evolutionary neural network and able to predict the what is the outcome and what is the pattern there involved in the melting side. Because what happens like if VIM processes are very lengthy furnaces, like a typical VIM heat takes more than 8 hours. So, but if you go to the shop floor and see, like it will taking a lot more than that. Like it is some heats may taking even 12 hours also, normal heats. So just we took that challenge upon us, and we just want to set that we want to able to reduce that like melting time of VIM managing steel there. So for that, we start exploring the data, and after that, we validated that with our test data also, and it is now some recommendations we have given after that. So this is the data set before cleaning. So you can all see, you can able to see that all these dots, like all these gaps are there in the data set. We have filled those gaps, and which are not possible, we have completely eliminated those gaps. So this is the data set there. This is the PPNNG. This is the Spirited Pre-genetic algorithm neural network. So this is the form it is taking. We have implemented, like it is written in MATLAB programming. So we have like that. So if you see the file here, you can see that like there are a lot of things like that sets log generation. Like you can see, you can check here what is the generation you want to use. Like you can set here the number of generations, the number of nodes. Number of nodes is the talking about the number of hidden nodes. So how many hidden nodes you want to take, like hidden neurons, how many neurons you want to take in the hidden nodes. Then this max rank is the Fonseca ranking. The killing interval is after like how many interval it will kill, that how this prey predator thing, how after how much iteration this will activated. This prey population size is there, like 300 population size is there, and this is the generation. This is generation means the iterations, how much iteration you want to perform. And this prey population size is that what is your neural network size you want to maintain there. So this is the prey population size. So with that, and there are a lot of other parameters are also involved there, and just giving us some glimpse of that. And with that, all this thing with this, we can able to like you have to do a lot of initial testing there, like to optimize to get the optimized result out of that. And this you have to play with all these generations, the number of nodes, then max rank, kill interval, prey population size, like that. So after a lot of involvement into this, you can able to see the predictions there. And this is the basic architecture that how it is evolving. Like you can able to see that in the first chart for the generation one, the prey population size what we said 300, it is coming around 545, and only 30 predators are there. And the best fitness among all the solution is achieved this 0.14318 is. So this when we do the fitness calculation is always on the solution we are taking. Suppose y1 and y2, if we consider, the best fitness is always taking as a min. Like if something is maximum you want to do, but you can always try to convert that into min side. So it will show you the best fitness of the solution at present. And this bottom side, it will give you the that complexity with respect to the connection, like all this error versus complexity chart it is giving. Like because you have the solutions of different network complexities, from basic network to very complicated, like very few connections to very high connections. So all these things are there. So how it is performing for the very high connection, how it's performing for a very low connection. So all these things, this complexity, you can able to see in these figures. Similarly, as I said, it is all having the training part and the optimization side, because ANN cannot do the optimization, it can only do the training. So this is first the training data set where the training is there. And once is there, this particular the there are some criterion like Akaiki criterion able to predict a particular solution, which is like all are this particular line. This particular line is all comprises of non-dominated solutions. But uh, to start for the optimization purpose, can choose a one particular solution out of that using some criteria called the Geikie criteria, and based on that it can able to choose so that it can able to perform the optimization task in the next step. So this is the optimization of the data model where it is all this predator genetic algorithm is taken care there. And it will take all the inputs, like all the trained files from the previous training data set, and it will take all the trained data set and do the like optimization of the trained data set for the two given objectives. And this is all the objective the optimization results. So our objective for this purpose was the refining time and the melt duration. Like melt duration was the prime one. Refining time we also took, because we have seen that refining is if we able to reduce the refining time, our melt duration also reduces. So these are all the input we have taken from our margin steel manufacturing. So this carbon added at start, cold decay. So these are all technical terms in primary melting part. So where we have taken all these inputs as a like inputs for this to given objectives for the refining time and melt duration, you can, and it can refine and the data and can able to predict you the like the dependency of that. Suppose carbon added start, it is having a negative impact on the refining but no impact on the melt duration. Cold regret has the positive impact side. Positive means it is with increase of cold regret, your refining time also increases. So it is having a positive impact. Negative means something on the vice versa. Some like inverse effect is there. If something is increasing, then the effect will be going down, so something like that. So this positive effect as they are negative, so mixed effects is having like uh, algorithm is not able to understand whether it is a positive or negative, so it becomes a mix. So these are all responses we can able to predict out of the of our input, and this kind of responses are very helpful because these kind of responses can give you a direct picture at how, because for these two parameters these many inputs are involved, but it is very difficult to understand each and every input, what is the role there. So this kind of approaches can give you a, some sort of analysis of each inputs, like how that input is related to the output variables. So this dependency and independent variable that all this you can able to map, like how independent variable is related to the dependent variables. So like this, and this is the Pareto we are talking about. So with the melt duration, refining time, both in mean. So this melt duration and this we are able to achieve a good Pareto optimality curve, and this particular line is comprises of all the non-dominated solutions there, and this is the fitting uh, during the training side. So one thing is very important here, that during the training side, because this is a industrial data, it is having a lot of we can say a lot of noises are there. So we have to avoid the noises also. So you can able to see that these experimented values, these red ones, and these are trained data. So you can able to see that this trained datas are not capturing each and every highs of this particular red data, because some data algorithm is identified as an outlier noise, so it is actually not capturing each and every part of the data, but it is capturing like most of the trend there, like it is capturing every trend here but not the very highs and very lows. Some highs and lows it is captured, it is assumed these are important and these are not the outliers, so it is capturing those trends, but it can not capture this suppose this negative side of that particular thing, so it is capturing the in between that. So with this capturing, it is can have only 63% capturing it can achieve, like 0.63 is there, so it can achieve only 63% capturing, and for similarly for the melting time, it is capturing around 69% of the data. And these are the response side of each and every optimized data. If you want to analyze that, so we did the analysis of each and every inputs. So these blue ones are the real experimented datas, and these red ones are data generated from the evolutionary algorithms. So these red ones you can able to see that in few cases, suppose this carbon in first sample, this in these cases it is showing that if you able to achieve a very low carbon is first sample, you can able to reduce your melting time and refining time, because your initial data is showing some variability, but the algorithm data is showing that if you are able to maintain a very low carbon in first sample, then you can able to achieve your melting and refining time very closely, like very efficiently. You can able to reduce it. Some similarly, this nitrogen, it is on the higher side. So few things you can able to see that you can able to predict very minutely, like uh, you can able to see that how there's variability there and how can able to predict that all those things, and how that input variables are that variability, like how algorithm is understood and how that affecting your output variables there. So we did some physical validation, and with the, our best melting practice, we said that uh, we consolidated a heat of 15 heats, and with that we have said we have like check with our recommendation that if we do that recommendation, we are able to the best melting practice, like we can able to reduce the melting time or not. So in most of the cases, we have seen that the best melting practice, if we take that part, we can able to see that the parameters which are involved in the best melting practice is actually matching with our results only. So you can able to achieve a very low melting time, very low refining time, and the carbonated are very high. So these cold liquids are not available. Like these are not able to map properly, and these are all mapped. Like if you're able to achieve these things very low, you can able to get a very good like melt like reduce, you can able to reduce your melting time and refining time. So all this like things are there, like this we have theoretically analyzed this output of the data, and we have given the recommendation based on that, and hopefully they are doing good. So that's all from my side. If you have any question, you can ask me. Thank you. Thank you very much.
Thank you so much, sir. So, sir, the participants are raising their hand. So, we will just.
Yeah, yes.
Good afternoon, sir.
Good afternoon.
Yeah, so I want to ask, why do we use get, sir?
Do we use?
Gets this or get and get like that. Why do
Oh
we
no,
use
no,
that?
I'm not. That is for the understanding purpose. Like these are very basic, simple understanding. To do very basic, simple understanding, we see. I cannot give you a calculation of very complicated uh, inputs. That is very becomes very complicated. I cannot able to perform physically. So, in order to perform a very basic calculations, so that for that reason this or gate outputs, like I have like given you that particular example, because those are very
Okay.
uh, yeah, this x1 and x2, only two x1 and x2 are there, and only like out of that only four outputs you can possibly get. So to give you that how that calculations is going on, I have given you very basic simple example. But these, if you check this
And this,
evolutionary algorithm calculation, these are very difficult. I cannot give you any calculations there.
so this feed forward propagation and back propagation will always happen together.
Always happens together. So
Even
if
in the
you
case of evolutionary neural network.
in case of evolutionary neural network also, but there is a catch there. Like during the training side, it this ANN, because ANN is mainly during the training side. But when we do the optimization side using the genetic algorithm, then this particular back substitution and this for feed forward is not there. That is something different. Like then there is genetic algorithm just taking care of all the solutions and everything.
Thank you so much. Do we have any other questions? Please raise your hand. Any questions from the participant side? So I think we don't have any further questions from the participant side. Thank you, sir, for your very insightful talk.
Thank you. Yeah. So if any participant want to like ask anything, I can share my email so that they can write directly to me. So if they are interested to understand anything and some they have missed something,
That will be
they
very
can always
useful
contact.
for us.
Okay, definitely, sir. We will share your email ID to the participants for any other further future interactions. Thank you,
Thank
sir.
you. I can leave now, right?
Yes, sir. Yes, sir. Sure, sir. Thank you, sir.
Okay. Thank you. Thank you. Yeah.
Okay. Thank you, sir.